Last video we introduced the concept of static equilibrium and the sum of forces equating to zero. And I touched briefly on the moment equation about how the moment's equal to zero. So I think I'll start off by concretely writing the equations down, and then we'll talk about exactly what a moment is. There we go. So the moment equations, similar to the force equations, are essentially just saying that the sum of moments about the z, y, or x-axis are all equal to zero. And you're probably wondering by this point, and probably from last video as well, what exactly is a moment? So in physics, moments are often referred to as torque forces, but essentially what it is it's a force applied over a distance. It's quite simple. We'll use my favorite example, the Cantilever Beam, to go ahead and look at what exactly a moment is. Okay, so here we go. Cantilever Beam. Okay, so same thing. Here's the beam. Let's ignore the weight of the beam real fast. Okay, so we can already go ahead and draw our reactions. Okay, again, at the wall, we know we have a reaction in y, we know we have a reaction in x, and we know that we have a resisted moment. And this is a 2D case, so we're not looking at the reaction in the z. And now let's go ahead and tack on a couple of forces here. Let's say we have an applied load P at a distance of L. Okay. Now we can easily solve for the reaction in y and the reaction in x, because we know that y must oppose P and there's nothing in x, so x is 0, neglecting the weight of the beam. However, let's say we had a more complicated problem, which I'll show in just a bit, where we didn't have enough information, we had too many unknowns. Then we would have to use the moment equation as well to help solve the problem. Now, a moment is simply defined as, if I'm taking, you can pick anywhere, any point on your body, but typically I like to pick reaction points, basically where things are pinned or supported. In this case, we always define our coordinate system. Let's define this as y, this is x, and let's say I'm taking a moment about point O. I'll call that point O. So let's say we take a moment about point O. Now the important thing to understand about a moment is basically a twisting force, a torque force, a bending force, however you want to think about it. It's essentially saying that if I have a load out here pushing down on my arm, that's creating a torque or a bending moment, is how we call it, about whatever point I choose. I mean, it's creating, in this case, I'm going to choose the point to be my shoulder. And you can see that there's a bending force applied, right? The force applied here creates a bending motion, a torque, however you want to visualize that, about a specific point. You can also take the point to be here, right? It would still be creating a moment about this point, right? It can be any point. However, a few characteristics of a moment. If I were to choose my point to be here, let's call this point A. At A, there would be no moment applied by P at A due to the fact that P goes through A. If you think about it, you can't have a twist if you have a force applied directly over your reference point. If I apply a force onto my shoulder right here and I push on this, it's not going to create a torque about anything, because that force is applied through the point. Okay? It's something very important to keep in mind when you're doing your forces. Is a moment, it took so long to write this, but I'll write it now. A moment is simply a force multiplied by the distance it's applied from your reference point. So your choice of reference point has to be very specific, I'll say. In this case, if I choose the reference point at O, there's only one force that can create a moment, aside from the resisted moment in O, due to the fact that only P applied over a distance. Only P is applied over a distance. all of these other forces act through this point right here and therefore will not create any moment. Hopefully that makes sense. So therefore, if I want to do a sum of moments to figure out what my resisted moment m is, I can simply say sum of moments in the z direction, because it's going to be about the z-axis. If you think about it, I'm twisting this way, which is about, it's a rotation about the z-axis, which is coming towards the camera. You can draw that out. That twist about the z-axis is going to be equal to the resisted moment m minus p times L. A little quick note about sign notation here. In engineering, we typically say that if you're rotating counterclockwise, you're inducing a positive moment, and if you're rotating clockwise, you're inducing a negative moment. We can see that here. Force P is applied, it's going to create a rotation like this. This is clockwise. And M, the way I've drawn it, is in the counterclockwise direction, hence my signs, positive and negative here. So of course you can solve this equation to say that M is equal to PL. And that's how you know what the resisted moment at the support is. Okay, so let's take this example. Again, we have a beam. It's supported by two pin supports. One of them's rolling, one of them's not. So the first step here is to identify what the reaction forces are, right? We know that a pin support can resist a force in the X and the Y, and that a pinned but rolling support can only resist the force in one direction. And neither of these supports can resist a moment. So we'll go ahead and we'll identify what those forces are on the diagram. And since I have two different reactions in the Y, I'll label them accordingly, RY1, RY2. Note that all of these are directly applied at the point. They're not actually applied out here. I simply do that to make it easier to see. So as you can see, we have three unknowns. Now I'm going to go ahead and I'm going to apply some forces onto this body separated by certain distances, and we're going to see the complication that happens. Again, three unknowns, we should need three equations. So let's see what happens. There we go. So I'm going to apply two forces, F1 and F2, separated by distance L. Now what you're going to see here very quickly is it's quite simple when solving the X direction and the reaction force in X. I have no force in X, therefore the sum of forces in the X direction is equal to 0, which is equal to Rx. And in order for Rx to equal 0, Rx must be 0. So that's quite simple. However, the complication now comes because I have two reactions in the Y and two forces applied. Of course, I know the forces, but I don't know my reactions. Again, in engineering, we're solving for reactions. So if I were to write out the equation for the sum of forces in Y, it would look something like this. And as you can see, we have two unknowns. We don't know what RY1 is and we don't know what RY2 is. Therefore, it's not possible to solve this equation for one solution, because I can put in an infinite number of combinations of forces for RY1 and RY2, and this could still equal 0. So we need an additional equation to constrain this to get a unique solution for RY1 and RY2. And this is where that concept of moments come in. So as you can see here, we have forces applied over distances. So I can pick a point, pick a specific point on this body at which I will have my moments about. And I can equate that to 0 because, again, if there's any point on this body where the net moment is not equal to 0, we're going to have a twist, we're going to have a motion, and therefore we will not be in static equilibrium. So I'm going to be very smart about how I do this, because remember, the rule with moments is anytime a force is applied through the point where the moment is taken about, those forces do not contribute to the moment. So I could, of course, choose this point over here, which would eliminate Ry1 and Ryx. That's a very good choice. Or I could choose this point over here, and that would eliminate F2 and Ry. So either of these things are going to basically help me eliminate the amount of forces acting on my body or that are going to create moments. If I were to choose a point like somewhere over here, I would have to use Ry1, F1, F2, Ry2 all in the problem, and it would make it a lot harder. So you really want to take your time and think about where you're going to take your moment about, because it will simplify your problem if you choose correctly. For the heck of it, I'm just going to take my moment about this point here. And again, pin supports do not resist moments. Therefore, there is no added moment I have to solve for in the problem. That's what allows me to solve this problem. So we'll go ahead and do that. The sum of the moments about point O, call that O, are equal to F1 times L in the counterclockwise direction. Look at the rotation. We're going to rotate this way, counterclockwise, which is positive. Distance L, force F1. And we also have Ry1 in the clockwise direction. Have to equal 0. And notice, there's no added m because, again, pin supports do not resist moments. So now that I have two equations and two unknowns, I can create a system of equations and solve for a unique Ry1 and Ry2. So this is how you can leverage the concept of moments to help you solve static problems. So we'll go ahead and we'll solve that out real fast. Okay. F1 over 2 is equal to Ry1, therefore I plug that in here. And then I can solve. And you'll see that if I solve this out, I'm going to get Ry2 is equal to F1 over 2 plus F2. And those are my solutions. So hopefully you can see how you can apply a combination of moment equations and force equations to solve a statically determinate problem. Quick note about statically determinate problems. If you have too many unknowns, obviously we wouldn't have been able to solve this. If we had basically, let's say, an extra reaction right here, an extra support, I would end up with 3 unknowns but only 2 equations to use. This would become statically indeterminate. We're not going to talk too much about that, but for all of these problems, we're going to create statically determinate problems, ones that are possible to solve. In order to solve statically indeterminate problems, you have to use the constitutive law and all of that stuff that we'll talk about later. Okay. So yeah, hopefully this makes some sense. Yeah, that's an introduction to moments.